How's it going, everybody? Mr. Dickin here. In this video lesson, we are going to be discussing how we could solve quadratic equations. Primarily today, I'll show you how to do these things by hand, but primarily we will be relying on graphing technology. So you know me, big fan of Desmos, all hail Lord Desmos. But if you've got a Casio or TI calculator, it'll work on those too. So things to keep in mind when we're talking parabolas, there's really only a handful of things that we can ask you for. So here's my made-up parabola. Ooh, fancy. We might be able to ask you for an x-intercept. And when we're talking word problems, those are particularly handy because that will tell us, when did something hit the ground? Maybe we could ask you for a y-intercept. And y-intercepts are particularly handy because that will tell us, hey, what was the starting height of something that maybe got hurled through the air? We could also ask you, what is the vertex? And that's going to be disguised as saying, well, what's the maximum height, or how high does this thing go if we're throwing or giving a trajectory of something? And how long does it take to get there if we're talking about feet versus time? So again, we'll do these by hand. Well, we'll do the setups by hand, I suppose. And then I have a feeling most of you, like me, will rely on good old-fashioned Desmos. All right, so here we've got a scenario. We have a graph showing a function of f of x, or y, equals negative 0.029x squared plus 0.59x, is modeling the height of one frog's jump, where x is the distance in feet from the jump's start. So there's our function, yay. And you can already see down below, I've got the Desmos screenshot pulled up. So the questions that you're going to be asked almost every single time is, how far did the frog go, meaning when did it hit the ground? How high did the frog jump, aka vertex? And what's a reasonable domain and range? And we'll discuss that here in just a second. So first, let's go ahead. Let's figure out how far did this thing jump. So we're going to find the x-intercept over here. Since this thing started off at 0, it's got a y-intercept. Even though it's not listed, I could pretend it's got a y-intercept of plus 0. Since it started off at the origin, we know it's going to start at 0. We want to figure out when does it return to 0. So here's how we could do this by hand. Well, first, let's set this thing equal to 0, right? If we're finding an x-intercept, we set this equal to 0. Now, these numbers are not pretty. All right, these are some nasty decimals. But since there is no y-intercept, there's no c value, I get to do a pretty cool shortcut. And again, this is only valid if you do not have a c value. Is I can factor this thing. And I realize some of you might be looking at me cross-eyed saying, how the heck are we going to factor, like, I don't know what multiplies to be negative 0.029. We can factor this left side by taking out a greatest common factor. And that greatest common factor is just going to be whatever my a value is and an x. So I'm going to pull out a negative 0.029x. Now when I do that, this first term will just become a 1x. The second term is going to be, well, whatever 0.59 divided by negative 0.029, whatever the heck that is. Fortunately, I've been graced with a calculator. So if I divide that out, I will get negative 20.344. I'll round that to just 0.34. And that whole thing is equal to 0. So now, using the zero product property, I can say that according to this first factor, x is equal to 0, and according to this second factor, x is equal to 20.34. So we just found our other x-intercept. Again, numbers weren't pretty, but as far as the math behind it goes, I would argue that that's not too terribly difficult. So we found how far the frog jumps, about 20.34. Did we do it right? Of course we did it right, because this is all pre-planned. Next, how high did the frog jump? Well, maximum height, aka vertex, we know how to solve. We can solve for vertex by using our good old friend x equals opposite of b over 2a if we were doing this thing by hand. My b value was 0.59, so negative 0.59, over 2 times negative 0.029. So we could math that out. Once we get our response, or our x value, we would plug that back in for x and see what we get. So again, we've seen problems like this where we're finding vertex values, so that's nothing too crazy. So that's how you do it by hand. Let's say you're lazy like me. You don't want to do it by hand. Good thing there's technology on our side. We can plug these things into our good old friend Desmos. So here I've got my function plugged in on the left side, and when I do this, I find the critical points, the x-intercept, the vertex, the y-intercept. Now the vertex is going to tell me two things. It's going to tell me both the maximum height, in this case 3, and then this is going to tell me the time at which it took to get there, or whatever the x value, x-axis, was referring to. So this might be horizontal distance, this might be time, whatever. So after 10 units, this frog was 3 feet in the air, and that was the highest height it reached. So how high did the frog jump? 3 feet high. Then it says, what is a reasonable domain and range for this function? Well, if I look at this graph, this parabola kind of gets graphed forever and ever and ever, right? There's little arrows on the end of this, so it would go on forever and ever. But realistically, we don't really care about anything other than this portion of the graph right here. Because anything to the left of the y-axis, well, that says we're either going backwards in time or backwards in horizontal distance. That wouldn't really make sense. Anything underneath the x-axis, well, if we're talking about height above the ground, this would be going underground. So that's not really going to be making sense for this. I guess you could argue maybe a frog can go underwater, but we really only care about this green portion here. So a reasonable domain is going to be just the x values from takeoff to land. And then our reasonable range would be starting height all the way up to the maximum height. So between those ranges there. So that's going to be our reasonable domain and reasonable range. With these, of course, you're going to use brackets because it actually does reach a height of, say, 3 feet, or it actually does hit that distance of 20.34 feet. Okay, next problem. The function is given for a path of a kicked soccer ball. Height is y, distance is x. So this one's comparing the vertical height, vertical distance, versus the horizontal distance traveled. And no surprise here, same old questions. How far does it go? Meaning, when does it hit the ground again? How high does it go? Meaning, what's the vertex? What's the reasonable domain and range? So 0 to whatever. Just like before, we could do these by hand if we wanted to. I could set this thing equal to 0, negative 0.03 x squared plus 1.6 x, set that equal to 0. Since there is no y-intercept, there's no c value, no constant, I can just factor out a common factor of 0.03x. And when I do that, I'd be left with x minus, let's see, 1.6 divided by 0.03. 53.3 repeating. So if I did not have any sort of graphing capability, I could still figure out my x-intercepts are 0 and 53.3. All right, so now we've done that by hand. Then we could find the vertex. Well, vertex, again, we can use the opposite of b over 2a. For this problem, our b value is 1.6, our a value was negative 0.03. So when we solve that out, when we do our calculations, I would get x equals 26.67 with rounding. I would then take 26.67 and I'd plug it back in for x and see what I get. That's if we're doing it by hand. Or we can use Desmos. All hail Lord Desmos. So here, I've plugged in my function. Some of these values, we already got those. No surprise there. We already knew 53.3 repeating. We had the x value for the vertex. If we plugged it back in, 21.3 repeating is what we would have gotten. So now we have every important facet of this parabola known. So we can answer the questions. How far does this thing go? Meaning, when does it hit the ground? That's that point over there. Well, it travels 53.33333 meters. Oh, I've been saying feet this whole time. Whoops. How high does it go? Well, height, that's vertex. Remember, vertex has two different values. If we're talking height, though, we want the y value. So the y value of that vertex, what was it again? 21.3. It goes 21.3 meters high. And then what is a reasonable domain and range? Remember, we only care about this graph when it's above ground and not going back in time. So reasonable domain and range are 0 to 53.3 for the domain and 0 to 21.3 for the range. Remember, domain is x's, range is y's. Uno mas. All right, we have a function. Negative 0.002 x squared plus 0.66 is the path of a softball hit for a homer. Nice hit, good job. F of x gives the height of the ball, and x gives the distance from where it was hit in feet. No surprise here, I've got the Desmos thing prepped and ready to go. If we wanted to do this by hand and we didn't have any sort of graphing capabilities, we could yank out a GCF of negative 0.002x. Inside parentheses, I would be left with plain old x minus, let's see, 0.66 divided by 0.002. Woof. 330. Hey, clean numbers, sweet. So by doing a GCF factorization, I can get my 2x intercepts. Nothing new there. If I wanted to find the vertex by hand, I could do my opposite of b over 2a. Wow, had a little bit of a moment there. So we could plug in our values for a and b from our function. We can get the x value of the vertex, take that x value, plug it back into the function to get the y value. Or we can go to Desmos. All hail Lord Desmos. One thing I should have mentioned earlier, and I forgot to, when you're plugging these graphs in, you're probably going to have to customize your axes so that way you can see things clearly. Desmos has little zoom in, zoom out buttons over here in the corner. You can also use the scrolling feature if you're using a mouse. If you hold Shift and hover your cursor over the x-axis, for instance, if you hold Shift, you're going to see a little icon that looks like that. And that will allow you to click and drag to scale only the x-axis. It'll leave the y-axis alone. You can scale only the x-axis. If you're using a touch screen to do this stuff, though, you can just kind of pinch and zoom accordingly on whichever axis you want. Anyways, I digress. According to this, we've got our vertex at 165, 54.45. Remember, this is a horizontal distance for the x. Sometimes x represents time as well, so be careful with that. And the vertical height of 54.45. So the height, the maximum height, is going to be 54.45 feet. The horizontal distance, when does it hit the ground again, is at 330 feet. That's when we have a height of 0, meaning it hits the ground. All right, so let's answer the questions. You already know what the questions were going to be. How far does it go before it hits the ground? Oh. Hey now. It's going to go 330 feet. I don't know why this thing is being, there we go, a stickler. How high does the ball go? AKA y value of the vertex after rounding 54.5 feet high, and the reasonable domain and range. We only care about this ball when it's above ground, and we're not going backwards or back in time. All right, folks, that is it. You know the drill. If you have any questions, please let me know. And as always, good luck, have fun, be safe, roll tide.